All right, thank you, everyone. Welcome. I'd like to acknowledge my co-authors, some of whom are in attendance today, and also thank AGU for having our talk. So as Robin mentioned, this talk is about the nexus of water availability, land suitability, and low-carbon technologies. And I'll really be continuing on the same theme as Robin about the value of geospatial analysis in evaluating the impacts of climate and climate policy. So the motivating questions for our research are really to look at what is the on-the-ground feasibility of future electricity system expansion under different policy scenarios, and specifically to look at what is the on-the-ground feasibility of the electricity system expansion that comes out of an integrated assessment model. So in the upper right there, you can see sort of the typical output of the GCAM model, the Global Change Assessment Model, which is a bar chart, again, showing the expansion of the system over time, showing the change in the technology mix. But that doesn't really tell us a lot about, can we actually site those power plants? Is there enough water to run them? Are there policy constraints? Are there other environmental constraints potentially limiting our ability to actually achieve the emissions reductions that are the goal of the RCPs? So what we want to do is actually translate that bar chart into a siting plan, such as you see there. So that our modeling work has done this, has coupled an integrated assessment model to a siting tool. And we're specifically looking at these three scenarios, RCP 8.5, the RCP 4.5. So the first one is a business as usual future without a carbon price. The 4.5 includes a carbon price. And then we're doing a sensitivity case where we say, what if the carbon capture and sequestration technology does not become widely available before 2050? So what would happen to the technology mix? How would that change siting requirements? We're using the Prima Framework, which is the platform for regional integrated modeling and analysis developed at PNNL with internal funding, large internal initiative, as well as funding from DOE and NGA, some funding from DHS, Office of Science, Office of Electricity, and EPSA. This has been presented in other formats, so I'm not going to go into detail about Prima right now, except to say that it is an integration of a dynamically downscaled regional climate model with a global and regional integrated assessment or macroeconomic model that evolves the energy economy over time. And then those two models drive detailed sector models that let us look at different sectors in more detail in geospatial space. So a little bit more behind the curtain, specifically for this research I'm talking about today, we have done a one-way coupling between the Earth system model, land surface hydrology, river routing, water management, as well as the integrated assessment model, which allows us to have consistency in the climate scenario and the economic scenario. So the RCP is driving through both of those high-level models down into these sector models, and then the siting model called SURF for capacity expansion regional feasibility is the model that operates at a 1 kilometer resolution and cites that integrated assessment plan given environmental constraints. So there are really two main components to the SURF model. There's a very large suitability database of GIS layers that includes a set of common layers for all thermal power plants dealing with protected lands. And then we have technology-specific layers that address specifics, like for coal-fired power, proximity to coal mines, proximity to transportation. We also deal with population density. And again, these things differ by different technologies, so there's quite a detailed database here that builds up a suitability map for different technologies. And as I mentioned, it is a dynamic model, so the model can evolve through time with changing population, with changing water and water availability that comes from the climate modeling. And again, the integrated assessment model steps through time. So the siting model steps through time in lockstep with the integrated assessment model. Should mention that for wind power, we're actually using the work done by our colleagues at NREL on wind farms. So the EWIT study specifies specific wind farm locations as opposed to in an integrated assessment model. Typically you'll have a continuous supply curve for defining your wind resource. Here we're going to compare and contrast the approach taken in the integrated assessment model for wind with having these discrete points of high-quality wind resource. The other piece of the siting model is an economic component. So suitability is necessary but not sufficient to really define a siting plan, and we're really trying to simulate the way a siting planner would look at where to put power plants across the landscape. So we're incorporating things like the distance to transmission, as well as the value of the power in different locations, which is a function of supply and demand. So we're actually integrating with a production costing model to get locational marginal prices for power of different capacity factors. So we use this concept called net locational cost, and the model essentially, once all of the suitability has been defined at 1 kilometer, then the model sorts through, in terms of net locational cost, all of those combinations of technology, grid cell combinations, and sites according to net locational cost from low to high. So here's an example of the results. On the left here, I'm showing the GCAM results for the RCP 4.5 versus the RCP 8.5. First, I want to point out the difference in the technology mix over time, and you can see there's a lot more nuclear with the RCP 4.5. That's because of the carbon price, encouraging the low emissions generation. And then in the rest of the mix, you can see in the 4.5, there is quite a bit of CCS technology that's come into the mix by the end of this period, compared to the 8.5, which is relying still primarily on coal and quite a bit on natural gas. So here's the result of the siting model. Now, I know I don't expect you to see all the differences. I'm not going to talk through these maps in detail, but with this wonderful large screen here at AGU, you may actually be able to see some differences between the scenarios, but I'll try to unpack some of these differences in the next few slides. But first, let me also contrast the RCP 4.5 scenario that we ran with the no CCS scenario. So if carbon capture and sequestration technology, if that technology does not mature and is not available to us, then what the GCAM model simulates is much more nuclear power being built, again, to try to get at that RCP 4.5 emissions reduction. And the rest of the mix, again, in the 4.5, you see the CCS technologies, excuse me. Without CCS, you see an increased reliance on natural gas as the only other option, really, to try to meet demand. And here are the siting model results. And again, here just you can see some general patterns, some differences in some of the technologies in certain states. I should say we feel like we've only really scratched the surface of delving into these results, because really one could look at this state by state, water basin by water basin, technology by technology, and see a lot of interesting differences between the scenarios. But the first one I'd like to just call your attention to is we did go in and look at how does cooling water availability change between the RCPs. So here's a picture of cooling water availability according to the Clean Water Act 316B for nuclear in the state of Florida. And what we're showing here is that in 2035, under RCP 8.5, we were able to put a couple of nuclear power plants here in Florida, but under the RCP 4.5, this area is not available because of cooling water, lack of cooling water. And that may seem counterintuitive, but under the RCP 4.5 compared to the 8.5, there's a much larger increase in agricultural demand for water. So we actually see a reduction in stream flow, a reduction in water availability, and that causes a shift in nuclear plant siting from this location actually over here when we look at the actual siting results. And then jumping back out to a big picture of what we could and could not cite in the siting model compared to what the integrated assessment model called for. On the left here, we're showing the number of unsited power plants, and on the right, as a percentage of what was called for, again, to meet the emissions reductions for the RCPs. And about 20% of the nuclear was unable to be sited. I'll show why in just a moment. And then about 30% or more of the wind farms were unable to be, of the wind power was unable to be sited, and we'll talk about that. So for nuclear, the reason we have that high unsited number of nuclear plants is because there are currently moratoria on new nuclear plants in many states in the United States. Here we're focusing on the eastern half of the U.S., but you can see in red here, these are the states with nuclear moratoria, but in the integrated assessment modeling, it's calling for nuclear in each of those states. So this is, an example of where the integrated assessment model could include those nuclear moratoria. It certainly has the technical capability to do that, but the global modeling assumptions have been that those moratoria will be turned over, all right? But what if they're not? So that's what we're able to show here, is that there will be real challenges in achieving RCP 4.5 greenhouse gas emissions reductions if these moratoria remain in place. You can see that there's about 2 nuclear plants in every state in the eastern half of the U.S. and more in Florida, and that's not addressing the fact that we couldn't put the nuclear we wanted to in those moratoria states. So there's either going to be a huge burden on other states to pick up the slack on nuclear power, or these moratoria may need to be rethought. On the wind farm side, what we see here is that, and again, the integrated assessment model is asking for more wind in certain states than is available according to the EWIT study. And recall, the EWIT study is discrete points. These are the highest quality wind resource in the eastern U.S. So what this is showing is that there's plenty of wind resource remaining in the plains, but unless we can actually move that power east with new transmission, we're not actually able to capture that low carbon benefit of wind power in the integrated assessment modeling. So just to finish up here, our future research goals are to implement feedbacks from the siting model to the integrated assessment model, to implement feedbacks to water management, and then also to address additional water-related constraints. My colleague Mohammed Hejazi will be talking later this week about some of the work we've done identifying water deficit hotspots in the U.S. Those are likely to affect power plant siting as well. And then we plan to expand the model to show the results for the western U.S. as well as outside the U.S. Thank you very much. It says I have 40 seconds for questions, so any questions? Yes?
Did you take into account the impacts of climate change, temperature, water availability, water temperature on siting, or is this just to meet CO2 reduction?
Right. We took, for siting, we did use the Clean Water Act rules that specify a minimum mean annual flow that depends on the withdrawal rate from the power plant. So we did that on a technology-specific basis, and the water availability was climate-driven. So whether it was an RCP 4.5 climate or an 8.5 climate. Any other questions? All right, thank you very much.